We spent the last few years typing prompts into a text box, waiting for a machine to react. Now, artificial intelligence is moving past the chat window, executing multi-step workflows across the internet without asking for permission. The generative boom from 2022 to 2024 established a clear baseline. Large models learn to assemble flawless sequences of language, generate hyper-realistic pixels, and synthesize high-fidelity audio on command. You can see this mastery in the top video generators. Google's VO3 prioritizes 4K cinematic polish and deep integration into production tools, while OpenAI's Sora focuses heavily on temporal coherence and simulating physical interactions over longer clips. In psychological terms, these early generative models function entirely on System 1 thinking. They are incredibly fast, are deeply intuitive, and highly reactive, relying on pattern recognition to formulate an immediate response. But an AI relying solely on System 1 has a severe limitation. It cannot pause to verify its own logic or adapt a plan if circumstances change. When confronted with complex math or multi-layered logic, it guesses based on probability, often leading to confident, seamless hallucinations. Earlier milestones in artificial intelligence worked entirely differently. When Deep Blue defeated Garry Kasparov in 1997, the machine relied strictly on rigid, brute force calculation to evaluate millions of potential moves. Generating a convincing paragraph or a cinematic video clip has incredible value, but it hits a ceiling. If an enterprise software system cannot internally fact-check its own logic, it cannot be trusted to execute a critical business workflow. To solve this, developers shifted the architecture toward System 2 thinking. Models like OpenAI's O1 and DeepSeek's R1 are designed to emulate slow, deliberate, and methodical reasoning. This diagram illustrates a process called test-time compute. Instead of burning all their processing power during the initial training phase, these models allocate a massive surge of energy and computational resources after receiving a prompt, during the actual inference phase. This extra processing time enables chain-of-thought processing. The model generates a hidden internal trace of its reasoning, splitting the input into multiple branching logic pathways to explore different solutions. As it explores these branches, it actively scores them. It recognizes flawed logic, halts those branches, and prunes them away, isolating the single verified correct pathway before generating its final answer. This architecture enables the machine to solve complex problems through active internal verification, moving beyond the simple statistical pattern matching of previous generations. Once an AI model can reliably reason, its role expands. It upgrades from a co-pilot that suggests text alongside a human to an agent capable of executing tasks autonomously. This flowchart maps the architecture of an agentic loop. It operates continuously through 4 distinct steps: perceive, plan, act, and observe, with a large language model pulsing in the center as the cognitive engine. During the act step, the language model reaches outside itself. It autonomously connects to external tools, querying a database, updating a CRM, or drafting an email, translating its internal plan into digital actions. The critical component is the observe step. The agent reads the results of its action. If a database query fails or a login is rejected, it detects the error and feeds that data back in, automatically formulating a new plan to try again. By 2026, the large language model functions as a modular cognitive engine, the core of a broader system designed for continuous, autonomous execution. Deploying this autonomous ecosystem relies entirely on a foundation of massive proprietary human data, creating severe legal friction. Major copyright lawsuits are actively working their way through the courts. Publishers like the New York Times argue that AI model weights have illegally memorized and reproduced copyrighted expression without permission or compensation. Regulators are stepping in to enforce transparency. Under the European Union's AI Act, providers of general-purpose AI must publish detailed, structured summaries of the specific data they use to train their models. Tech companies are attempting to manage this liability by embedding provenance systems into their outputs. Google injects invisible SynthID neural watermarks directly into its media, while OpenAI utilizes C2PA metadata to track the origin of generated files. Legal disputes over training data now act as the primary limit on agentic AI growth. potentially stalling deployment even as hardware efficiency continues to climb. Economists estimate Agentic AI will permanently increase global GDP by 1.5% by 2035, affecting 40% of the economy. Integrating this creates a distinct productivity curve. Workers initially experience a learning tax, a temporary dip in output, before eventually achieving a 20% net speedup. Measured, this automation provides a disproportionate performance boost to lower-skilled workers, rapidly narrowing the human skill gap across highly technical professions. Production teams in 2026 are deploying proactive digital coworkers that plan and resolve tasks autonomously, moving past the reactive text interfaces of the early 2020s. Artificial intelligence now operates as an autonomous layer of infrastructure, maintaining and managing complex systems without direct human intervention.